In the last part of the chapter, we look at energy and power in circuits. So let's come back to these light bulbs right here. So I've got a 60 watt bulb and a 100 watt bulb, and the top terminal on both bulbs is connected to 120 volts. The bottom terminal is 0 volts, and so I've connected them between these two different voltages. There's a potential difference across the bulb, and when I connect the circuit, charges will flow, there's a current in the bulbs, and because there's a current in the bulbs, the light bulbs light. And so this is a version of our standard model of circuits. And we've seen the 100 watt bulb is brighter. And we have equations for power in circuits. Now both of these bulbs are connected across 120 volts. And the bulb with the higher resistance is dimmer than the bulb with the lower resistance. And we can see that by looking at the equations for power. And so this bulb has more current, this bulb has less current, this bulb is brighter, this bulb is less bright, this bulb has lower resistance, this bulb has higher resistance. And we have relationships that explain all of that. But now I'm going to do this. I'm going to take these two bulbs and hook them up in a circuit where they're connected in series. So the 100 watt bulb and the 60 watt bulb are connected one after the other. The current goes through this one and then it goes through this one. Now think about this. Think about this. The same current goes through this bulb and that bulb. The 100 watt bulb has a low resistance. The 60 watt bulb has a high resistance. They have the same current through them. Given that, when I turn on the circuit, so the current flows inside both these bulbs, which will be brighter, the 60 watt bulb or the 100 watt bulb? High resistance, low resistance, bulbs have the same current. Which bulb is brighter when I connect them in series? We'll give you some choices. Well, if the current in the two bulbs is the same, that tells us that the bulb with the higher resistance should be brighter, because we have an equation for power, and if the current is given, power is I squared R, big resistance means big power. And so when I hook them both up in series, the 100 watt bulb barely lights, the 60 watt light bulb is much brighter, and it's brighter because it's got higher resistance. Now notice this, both bulbs are dimmer than they were before. The total resistance of the circuit is greater, and so the current is less in the circuit as a whole, so the bulbs are less bright. And this bulb is brighter, and it's brighter because it's got a higher resistance. Now this question of passing an electric current through things as an energy transfer is extremely practical. Energy comes in and is dissipated as heat inside these light bulbs. Warms up the filament, causes it to give off light, but there's all sorts of ways that you can use this. And we'll see several different examples in the chapter. But here's one that's very kind of amusing and very practical. This is a device called the hot dogger. These two terminals, when I plug them in, are separated by 120 volts. And if I take a hot dog and I connect it between the two terminals, and I connect it up, current goes through the hot dog. When current goes through the hot dog, it's dissipated as heat, and the net result is it cooks. And this was convenience cooking from the 1970s. Now in the next chapter, we're going to look at more complicated circuits that involve multiple resistors and capacitors, complicated circuits, and all the different things that you can do with them, and we'll do that in the next chapter.